So let's look at our data and our observations from yesterday and make some conclusions about what we saw in that activity. In order to get your done stamp on this, by the start of the next class period, you must have those questions that I provided to you answered thoroughly and completely. And let me clarify, that doesn't mean you just write down the annotations that you see me putting on the screen. Those are going to be very, very brief, very, very summary, just to help the discussion. You must thoroughly and completely show that you understand what I am presenting to you, and I've got to see it on that paper in order for you to get your done stamp. First of all, why is the work straight up not equal to the work using the ramp? Well, remember, work is doing a job, and the job in this case was getting this block up to whatever height that you chose to set the ring stand at. And I'm going to pick up just a random number. Let's say that was a 100 joule job. Well, when you use the ramp, in essence, you did the same thing. You got the block to that point. And we know that's 100 joules worth of work to accomplish that job. But when you did your math, you did your force up the ramp, and you did whatever distance it was up the ramp, you probably got something like 110 joules. You got a little bit more work. Now, why is the work going up the ramp not equal to the work of what the job is? Because when you go up the ramp, you have to fight friction. You do a little bit of work when you drag that block up the ramp in fighting friction. So not only are you doing the 100 joules worth of work to get the block to whatever height it is, you're also doing work in overcoming friction. Now, let's look at the three different arrangements of the ramp. And what do you notice about the work in all of these situations? The work should be the same. Now, you might get some slightly different answers depending upon rounding and math and how you're holding this ring. But if it was 110 joules worth of work to drag it up that ramp, it should be 110 joules worth of work to drag it up that one, 110 joules to drag it up that one. If your numbers weren't exactly the same, they should have been kind of sort of close, and they all should have been more than the work of lifting the block straight up, because in every case, you have to do a little bit of work to overcome the friction, as well as doing the work associated with the job. Now, the question becomes why? Explaining the observation. We understand why there's more work when you drag it up a ramp, because you've got to fight friction. But why is each ramp about the same amount of work? Doesn't friction change? The answer, of course, is yes. So friction is going to change going up these ramps. This is going to be the most, and this is going to be the least, because as that angle of the ramp changes, the normal force changes, and when the normal force decreases as the ramp gets steeper, the friction should go down. True. So you should be thinking, well, wait a minute, over here I should be doing less work, right? Because I've got less friction to overcome. But you also have to apply more force because the ramp is steeper. Remember that work is a force times a distance. So over here, you're applying more force. You're also going a shorter distance. So even though the ramp is changing, there are other variables that are also changing. The amount of frictional force and the force that you have to pull up the ramp and the distance you have to go up the ramp. But no matter what the combination is, the work that you do ends up being about the same, because in the end, you're doing about the same job. You're getting the block to the top of the ring stand. Now, would changing the ramp material change the amount of work that you do? Well, if I change what the ramp was made out of, I'm going to change the friction. And if you notice, if this were a rubber block on a concrete ramp, there's a pretty high coefficient of friction, and friction is going to be really, really big, and you're going to have to do a lot of work to overcome that increased friction. However, if we had Teflon on steel where the kinetic friction is really, really low, you don't have to do much work to overcome friction. So the work you do depends upon the friction, and the friction depends upon the types of surfaces in contact. So changing the material of the ramp and or the thing being moved up the ramp would change your work. This is why you wouldn't want to try to slide rubber box up a concrete ramp. Think about what most ramps are probably going to be made out of. They're going to be something like metal ramps, where the coefficient of friction is a little bit lower, so things will slide better. Now, would changing the ramp material change the efficiency? Remember, efficiency is the ratio of your work to the work of the job. Well, the work of the job is going to be the same because in the end, it's the same work. The output, the work from the job remains the same. It's still the block going to that height. But the work you're putting in will be different depending on the friction. So if the work that you're putting in changes, the efficiency is going to change. So a slicker ramp, something with less friction, is going to be more efficient than a ramp that has a lot of friction. So why use a ramp at all? Well, honestly, in this case, you could lift the block straight up. It wasn't that heavy. You could physically get the block from here to here without the aid of a ramp. But if this was something that was really, really heavy, and to lift it straight up, say you had to have 500 newtons of force, and you couldn't apply that much force. You physically can't provide that much force. If you use a ramp, you can get the job done with less force because you're not lifting straight up. The ramp is supporting some of that weight. But what's the trade-off? Remember, work is force and distance. So yeah, I can use the ramp and I use less force, but I've got to go a greater distance. And that's the trade-off with using a ramp to do some work. In this case, in the lab, yeah, you don't need a ramp. But if this were a really, really heavy box, you might have to use the ramp because you can't provide enough force, but then you got to go a greater distance. Now, the maximum value for efficiency, theoretically, is 100%. The work that you get out of the ramp, the work that you get out of the job is whatever the job entails, right? It's a 100-joule job. You can't get any more work out of it than that. We've seen that the work that you put in is generally greater than the work you get out because you got to overcome friction. But in theory, if all of your effort is used just to do the job, you could have an efficiency of 100%. Unfortunately, that's never the case. The realistic value for efficiency is always less than 100 because you are always going to fight some friction. You're going to do some work to overcome friction. Theoretically, and actually, even lifting a box straight up without the aid of a ramp, you're not 100% efficient. There's some friction. When you lift something straight up, there's some air here that you have to move out of the way as you lift the thing up. Now, that takes a little bit of work, not much, but it takes a little bit of work. When you lift something straight up and you're using your arms and your arms are bending, there's a little bit of friction in your elbow joint, in your finger joints, and in your muscles. So nothing is 100% efficient. So efficiency in real life is always going to be less than 100. Now, think about a car engine. Car engines do a job for us. They move us from point A to point B. We put gasoline in there, and the gasoline releases its chemical potential energy, and we use that energy to do the job that we want it to do. But cars are only about 30 to 40% efficient. Every gallon of gasoline, you only get about 40% max of the work out of the energy that gasoline provides. The question is why? Remember, it's all about friction. That's the first place we go. When we look at all of these parts in a car, there's a lot of moving parts in contact with one another. I mean, there's a lot of friction in a car. And every place you have friction, you're doing some of your work, you're using some of your energy to do work to overcome the friction. And with so many moving parts, you lose a lot of your energy. Cars are not very efficient. The second problem with a car, with what we call a heat engine, is when you release the energy in a gallon of gasoline, you release that chemical potential energy, a lot of it is given off as heat. You know that car engines get hot. So not only are you fighting friction, you have all of this energy that was released and it's just given off to the surroundings. It makes the air, it makes the metal, it makes the car hot. Well, all of that energy is not being used to do the job that you want, which is move from point A to point B. So it's kind of wasted energy. And that wasted energy is a description of what efficiency is. It's how much work are you doing to do the job that you want to get done? How much of your energy is being used to do the job that you want to get done? So how can efficiency be increased? Well, it's primarily about the friction. This is why we use things like lubricants and oils. They make things smoother. They make things slippier. So when they slide past one another, they slip instead of grab, and you reduce the amount of friction. And if you can cut down the friction, you can increase the energy efficiency. You can not waste so much energy fighting friction. And this is why we put axle grease on the axles of our cars. Why we put oil in the engines of our cars. So at this point, that's the end of the presentation. Show me your thoroughly completed and explained answers in order for your done stamp tomorrow.